Welcome to lecture 4 in week 6 of machine learning foundations. We are going to continue the discussion of PCA, principal component analysis, and since this is an involved topic, we have split this across 2 lectures. In the last lecture we started with saying what for a given data set and a given input parameter, which signifies the load, which signifies the dimension of a lower dimensional subspace. We defined what reconstruction error is, and we are trying to figure how to find the best low dimensional subspace to project the data onto so that the reconstruction error is minimized. In this lecture, we'll continue this discussion and wrap up and arrive at the algorithm for doing this dimensionality reduction the PCA way, and that will involve picking some eigenvalues and eigenvectors of a matrix for certain matrix, and picking a subset of them and using that to do work out the projected data points. We'll look at that in detail today. After that, we'll look at an example to see all these ideas in action, which is in particular for a very simple example. We'll see how to apply the PCA algorithm to understand all the main ideas underlying PCA algorithm.
Consider a simple case to understand how to choose use. Before that, want to choose um plus 1 to ut such that J star is minimized. That's the goal. Now, to do this, I'm going to take a much simpler case. Consider the following simple case. Minimum just one u transpose cu such that u transpose u equals 1. Now I'm going to show you a tool, but I will try to do some explicit calculation using calculus also. But the most general approach for such constraints, so this is what is called as a constraint problem, constraint optimization problem. And the way to go about solving this is by using what is called a Lagrangian. Lagrangian L of u comma lambda, it has two parameters. U is the primal variable and lambda is called the Lagrange multiplier. This is the primal variable and this is called the Lagrange multiplier. So what you do is this, you take the objective u transpose cu. So you convert this constraint optimization problem into something that is unconstrained by throwing in what is called a Lagrange multiplier. Okay, this is what you do such that u transpose u equals 1, or now this constraint can be written as u transpose u equals 1, or equivalently 1 minus u transpose u equals 0. And that's the constraint for writing down the Lagrangian has to be in the form of either equal to 0 or it should be an inequality constraint, and that's the reason why we take this form. Now what you have to do is you have to take the Lagrangian and differentiate it with respect to u and equate it to 0. This implies, what do you get? This implies Cu equals lambda u, or u transpose Cu equals lambda, and that's really the solution. So min over u transpose Cu such that u transpose u equals 1 is lambda. Now you want to minimize this, so just pick the smallest lambda. Yeah. Now the important factor is, let's understand this. So C is this matrix, if you recall. And this is a real symmetric matrix. What does that mean? Which in turn implies all eigenvalues are real plus there exists a orthonormal is the smallest eigenvalue lambda of C. So that's the minimizer. U transpose CU equals lambda, and you just have to pick the smallest such. I mean, understand this, so maybe I have to do some explanation. So we just figured that if you see here, we got U transpose CU equals lambda, and so when I want to minimize this, when I want to find the smallest such U transpose U, when I do that minimize U transpose CU, then I have to just pick the smallest lambda. So the lambda is an eigenvalue of C. So take all the eigenvalues of C and pick the smallest one, and that would minimize U transpose CU. So there is to it. Now we come back to the original matrix C. So the original matrix C in the case of PCA is this, and there exists an orthonormal basis of eigenvectors. Okay. Let this. Now what is C? What is the dimension? It's a D cross D matrix. Basis B. U1 until UM, UM plus till UT, corresponding to eigenvalues lambda 1 until lambda n, lambda n plus 1 to lambda d, where lambda 1 greater than equal to lambda 2 and so on until equal to lambda d. So lambda 1 is the largest eigenvalue and lambda d is the smallest. Now if you want to, so just to recap this whole thing again, just follow this train of thought. The logic is that you are trying to minimize J star equals this summation, whatever is highlighted in this red box. Now if I take a much simpler case where there is just one term and I want to minimize here, as I've highlighted here, the constraint optimization problem, then it turns out to be the smallest eigenvalue of C. Now the way to go about this is, so if I want to minimize this, I take the smallest eigenvalue and the corresponding eigenvector out of the equation, and I can extend this logic to greater than 1 also. So coming back to, so to minimize, the main point of this is to minimize J star equals summation J equals m plus 1 to d of uj transpose C uj. All you have to do is choose um plus 1 comma ut. To be the to minimize this over um plus 1 until ut, choose this to be the d minus m eigenvectors corresponding to the d minus m least eigenvalues, that is say lambda m plus 1 until lambda d. Now the remaining u1 until um are chosen to be the top n eigenvectors of this matrix C. So that's really the PCA logic. So to summarize, so what you do with PCA is given data x1 to xn, xi belongs to Rd, Ri. What you do is choose form form the average point 1 by n equals 1 to n equals 1 to xg. Once you form this, form the matrix C 1 by n summation xi, let me call this x. Xi minus x bar into xi minus x bar transpose equals 1 to n. Third step, find eigen values and till lambda d, lambda 1 is equal to lambda 2 lambda d with corresponding eigenvectors, say u1 until ut. Here's what you do. Now the next step is from the projected data as follows. Projected data as follows. Xi tilde equals summation j equals 1 to m xi transpose j into j plus summation m plus 1 to d x bar transpose uj into uj. So this is the PCA algorithm, if I want to call this. And that minimizes this reconstruction error, which is denoted by J star. Okay. Let's do a simple example to illustrate the main ideas behind PCA, the algorithm itself. So consider the data. Say it's a simple example. You have data like this. And 0, 0 and 1, 1. Let's call this x1, x2 and x3. Now let us project D onto m equals 1 dimensional subspace. Okay, so to go about this, let's first understand what is x bar, which is 1 by 3 summation xi. Given this data, it's easy to see that it's already centered. So this is 0. Now what is the C matrix? If you know, this is 1 by 3 summation I equals 1 to 3 xi minus x bar to xi minus x bar transpose, which is the same as 1 by 3 xi into xi transpose. Now this is going to be 1 by 3 into what is xi minus first point into this plus the second point is 0. The third point is 1, 1. Now this turns out to be just 2 by 3 into 1, 1, 1, 1. So you got C. Now what is the next step to do? Calculate the eigenvalues. Eigenvalues of C. This turn out to be lambda 1 is 4 by 3, lambda 2 equals 0. Now corresponding eigenvectors, we actually need only anyway, we can calculate both, but I think we need only one of them. U1 is 1 and normalize it. It is 1 comma minus 1. These are things that leave us homework. We're not going to do this. Now what's the, so we need to, what's the best 1D space is spanned by U1 because that's corresponding to the largest eigenvalue, which is the same as this. Now given this, what is the projected data? Projected data is given by what is xi tilde. If you recall the formula, xi tilde is x1 tilde u1 into u1 plus x bar transpose u2 into u2. Now this is where I am saying x bar equals 0. So it just comes down to xi actually. Xi transpose u1 into u1. So what is x1 tilde? X1 tilde is just half minus 1 plus 1 into 1 1 into 1 1. This turns out to be this. x2 tilde is easy to calculate, it is 0. What is x3 tilde? This is just 1 1. What have you observed? No. x1 tilde equals x1, x2 tilde equals x2, x3 tilde equals x3. If the data is already on a one-dimensional space, then PCA is not doing anything different. Now what is the reconstruction error given this observation? This is something that you can directly say. The reconstruction error is just J star equals 1 by 3 summation. I think there is a summation I have added. Okay, anyway, it doesn't matter. Which is just 0 simply because of this and because of this. Yeah, so as simple as that. So if the data is already on a line, there's not much work to do. You can directly observe that the given data is already one dimensional, so you don't have to so PCA would not do anything odd, it will just retain the data as it is. Now this was a very simple example.
Okay, a summary of today's lecture, which was really tied to the previous lecture in the sense that we started the discussion about PCA in the last lecture, we continued it today, and we finally arrived at the PCA algorithm, which in essence is about doing dimensionality reduction by picking certain eigenvalues and eigenvectors, and using these eigenvectors you perform projections onto a low dimensional subspace, such that we actually showed that such a scheme minimizes the reconstruction error, and we also illustrated these ideas using a very simple example, two-dimensional example. In the next lecture, we'll look at an alternative equivalent viewpoint of PCA as maximizing variance of the data, and we'll see that the same algorithm can be viewed as maximizing variance or minimizing the reconstruction error. We've already seen the minimizing reconstruction error viewpoint in today's and the previous lecture. We'll look at the maximizing variance viewpoint in the forthcoming lecture.